Hello and welcome to helpyourmath.com. In this video on right triangle trigonometry, we are going to look at applications of trig functions. But before we get started, just two things to note. One, I would like to review the three main trigonometric functions when we're dealing with right triangles. So if we have a right triangle, we have one right angle and two acute angles. We pick one of the two acute angles that we're going to be dealing with, so we're going to use this one and we're going to call that one alpha. And then based on where alpha is located, we name the two legs based on where they are compared to alpha. So this one over here is the side that's opposite of alpha. This is the opposite leg, but sometimes we say opposite side. And this one down here is the adjacent leg. The one that's opposite the right angle is always the hypotenuse. And when we are talking about right triangles, the hypotenuse will always be adjacent to the angle. The adjacent side is the leg, not the hypotenuse. Okay, so based on the position of our angle, which I'm calling alpha, we can create the three trig functions, the main ones, based on the ratios of the sides. So sine of alpha is equal to the ratio of the opposite side over the hypotenuse. So the sine is always the ratio of the opposite side to the hypotenuse. Cosine of alpha is the adjacent side, it's the ratio of the adjacent side over the hypotenuse. And tangent of alpha is the opposite side over the adjacent side. So sine, cosine, and tangent are all ratios. They're all ratio functions. We want to remember this and cherish this. So one way that we do that is we use the acronym or the mnemonic device SO, CA, TOA. So SO, CA, TOA. SO is S over equals O over H. So CA and TOA. So we just want to keep that in mind as we go through these problems. One other thing is we are going to need a calculator. Sine, cosine, and tangent are almost always irrational numbers. So we are going to end up rounding a lot in these examples. Make sure you have a calculator, a scientific calculator that does have the sine, cosine, and tangent functions on it. Another thing that's really important for our calculator is we need it in the right setting. When we're talking about right triangles, we usually are dealing with the angle measures given in degrees. We want to make sure our calculator is set to degrees. Right now, this calculator is not in the right mode. We have it set to radians. So what we want to do is we want to hit this, on this calculator, we would hit this DRG button. That's going to switch it from degrees to radians to gradians. And what we'll see when we pull that up is it's going to say DEG, then we're going to have RAD, and then we're going to have GRD. We're going to ignore that GRD. Right now, it's underlined radians. We want to use this arrow key so that way the degrees are underlined, and then it should be all set. You can just quit from there. I think you can hit clear, or maybe you can hit second equals, and that will take care of that setting. So we want to do that, switch it 2 degrees. Once you do that, the calculator should have a little DEG at the bottom instead of the RAD. Other calculators might just have the letter R. You want to make sure you see the letter D. See the letter D or some indication that your calculator is in degrees? Okay, great. Let's look at our examples. Our first application, a 40-foot long escalator rises from the first floor to the second floor of a shopping mall. The escalator makes a 37-degree angle with the ground. What is the vertical height between the first floor and the second floor? So with these applications means we get to draw pictures. And if you know me, you know that I'm terrible at drawing. So laugh along with me as I attempt to draw an escalator, because even that is a little bit too much for me. Okay, so we have our escalator. We're just going to focus on the footing of it. Oh, that is just gorgeous. There's the landing of the second floor. Here's the first floor. And what we're really concerned with, not the steps necessarily. We're just going to kind of put a line through there, which would be underneath the stairs. We're going to deal with that line. We know that this escalator is 40 feet. So we're going to put 40 feet here. And what we're interested in is the vertical height. So we're going to extend the floor of the first floor over, and we're going to drop a perpendicular down. That's going to create a right angle with the ground. So that's what the vertical height is. It's from the second floor to the first floor when you drop a vertical. We also know that the escalator makes a 37-degree angle with the ground. So that's going to be right here, this 37 degrees. This is the ground, that first floor. And we're interested in the vertical height, so our unknown is over here. Okay, based on where the angle is, so the angle is over here. Our unknown is the leg that is opposite the angle. And the 40 feet would be the hypotenuse, right? It's opposite the right angle, so this is the hypotenuse. So we want to use the trig function that relates opposite to hypotenuse. And in case we forgot, let's write down our SO, CA, and TOA. And which of these do we want to use? We have opposite and hypotenuse. We want to use sine. So we would say sine of our angle, 37 degrees, is equal to the opposite side, which is our unknown, over the hypotenuse, 40 feet. I like to keep my answers exact. So I'm going to keep sine 37 because I know that's some irrational number. I'm going to leave it sine 37 until I'm ready to do my final calculation. To get x by itself, I need to multiply both sides by 40. So I'm going to multiply the left side and the right side by 40. Those are going to cancel here. And now I have my final calculation. It's 40 times sine of 37 degrees is going to give me that vertical height that I'm looking for. When I punch this in my calculator, I get something like 24.0726, blah, blah, blah. I'm going to round this to 24.1 feet. Since it doesn't tell me what to round to, I'll just round to the 10th place. And that's it. That's our vertical height. Now, did you do this calculation, but you ended up with negative 25.7415, and you're saying, that's close enough? No, no, no. You have it set to radians. Go back, set it to degrees, and try again. Make sure you get the 24.07 blah, blah, blah. Negative 25 is not going to cut it. Okay, how about our next example? A kite is tied to the ground. The string of the kite makes an angle of 64 degrees with the ground. If the height of the kite from the ground is 72 feet, then find the length of the string, I think that's supposed to say then, rounded to 2 decimal places. Okay, this time it does tell us it wants us to round to the 100th place. Now, one assumption we're making is that it's a very windy day outside, and so the string is taut, meaning it's tight and it's going to make a straight line, right? Because string could kind of be like all over the place, making whatever shape we want. We assume it's windy enough that it's a straight string. Okay, so we have a kite, another one of my exemplary drawings here. Boop, boop. I'm going to give it a bow tie. Oh, that's just perfect. Okay, and it has a string that's tied to the ground, so it's going to be tied with a stake. We'll put a stake in the ground there. Great. What do we know? That it makes an angle with the ground, so we're going to do this. And this triangle is clearly not drawn to scale because this is definitely not 64 degrees. Don't quote me on that. This is subject to interpretation. We also know that the height, if you're looking straight up and you're like an ant on the ground, so you're low to the ground, you're looking up 72 feet to see that kite. So that's going to be 72 feet. We want to find the length of the string, so our unknown is right here. Okay, so we have our angle. Based on the location of our angle, this is the side opposite our angle, and x is our hypotenuse. So again, what gives us the ratio of opposite to hypotenuse? Well, when we look at SO, CA, TOA, oh, it's right there. I don't even have to write CA or TOA because we have our opposite and our hypotenuse. So to set up the calculation, we're going to say that sine of the angle, sine of 64 degrees, is equal to the opposite over the hypotenuse. And we have a little bit of work to get x by itself. X is currently in a denominator, which is kind of problematic. If you want, what some people like to do is just put this over 1, so that way we can just do cross products. So we could multiply, and we end up with x times sine of 64 degrees is equal to that other cross product, 72 times 1, which is just 72. Now to get x by itself, it's being multiplied, so I want to divide both sides by sine of 64. And again, if you want to convert this to its approximation, you can do that and use the approximation. I just leave it for the end. Okay, these cancel. Great. Now I have x is equal to, and in my calculator, I want to do 72 divided by sine of 64 degrees. And when I do that, I get approximately 80. I'm running to 2 decimal places, 80.11 feet. So the length of the string is about 80.11 feet. Now, does it make sense that the hypotenuse is a longer measure than that vertical height? Yes, it should be. If you got something shorter, if you got 63, something went wrong because the hypotenuse should be the longest side no matter what. Okay, how about this example? I suggest you pause the video and try this one on your own, and then we can see if we agree. While you're doing that, I'm just going to go ahead and write my SO, CA, TOA up here. Okay, this one says Natalie stands at the ground level 400 feet from Fitterman Hall. All right, so we have Fitterman Hall. It's going to look like this. It's a really tall building. There's a door. There's some windows. Okay, gorgeous. Oh, and Natalie's over here. And we're going to just kind of like disregard her height for this because I know it does make a slight difference, but we're going to just not worry about that. Okay, so she's standing 400 feet from Fitterman Hall. Whee! This is 400 feet. When she looks up to the top of the building, The angle of elevation is 57 degrees. So the angle of elevation is like if you look straight in front of you and then you tilt your head up, the angle between when it's eye level and when you tilt it up is called the angle of elevation. So if this is her eye line here, then this is that angle of elevation that we're referring to, and this is 57 degrees. So that would be the angle of elevation. We want to know what's the height of Fitterman rounded to the nearest tenth. So we're interested right here in that particular value. So let's see, we have 57 degrees here. This is the side opposite or the opposite leg, and this is the adjacent leg. So which trig function relates opposite and adjacent? That would be our good friend tangent. So we're going to say that tangent of the angle of 57 degrees is equal to the opposite side, which is our unknown, over the adjacent 400 feet. We want to get x by itself. It's being divided. To undo division, we will multiply both sides by 400. And now we have our adorable expression to plug into the calculator. 400 times tangent of 57 degrees. And we get approximately 615 point, what are we rounding to? Nearest tenth. I get 9.4, so the 9 would stay a 9. And we get 615.9 feet. So the height of the building is about 615.9 feet. All right, very good. One more example. You're doing great. Devin is standing on top of the Empire State Building. His angle of depression is 72 degrees to his book bag, which he now realizes he left behind. The height of the Empire State Building is 1,250 feet. As he races back down, how far is he from his book bag once he reaches the ground level? Pause the video, try this one, see how you do. First, let's draw our Empire State Building, and as we know, I am terrible at drawing, so yeah, this is gonna be stellar. All right, here it is. And up here, there's an observation deck that goes around the Empire State Building, right? And Devin is standing right here at the top of it. Okay, so there's Devin, and his backpack is over here on the ground. There it is, and it has a shoulder strap. Okay, so the angle of depression. The angle of depression is similar to the angle of elevation. It's like he's looking straight, so he's looking straight and there's nothing really to see. Maybe there's some building tops he sees. As he tilts his head down, the difference between that straight and the down would be the angle of depression. Now, that's great and all, but we don't really want to use that value. So I'm just going to do that. That's his line of sight. This is how he's looking down. He sees his backpack. No good. We also have the distance from the Empire State Building to the backpack on the ground level. We're going to, forgo all the buildings that would be in between his backpack and the Empire State Building. Now, there's this geometric property that says if you have two parallel lines, which his line of sight and the ground would be, then this angle here, which is his angle of depression, is equivalent to this angle here. So those would have the same measure. We're going to use this 72 degrees. That way we can use the height of the building as well. Okay, so we have the 72 degrees, and the height of the Empire State Building is 1,250 feet. And what else do we want? Oh, so he gets to the bottom, right? He takes the elevator down. Now he's sprinting straight to his book bag. Nothing's in his way. How far is he going? That's our unknown. Okay, so we have our angle over here. This would be the side opposite the angle. And this is the side adjacent, right? We're not using the hypotenuse in this case, which means we want to use our friend tangent. So we're going to say tangent of the angle measure, tangent of 72 degrees, is equal to the opposite side, 1,250, divided by the adjacent, which is our unknown. This is another one, our variables in the denominator, so we might want to create a ratio here where we can cross multiply. So we have x times tangent of 72 degrees is equal to 1,250 times 1. Now to get x by itself, we can divide both sides by tangent of 72 degrees. 72 degrees. And in our calculator, we end up with, when we divide 1,250 by tangent of 72 degrees, and it doesn't say where to round, so we're going to just say 406 feet. He had to run 406 feet to be reunited with his backpack. These have been examples of applications of right triangle trigonometry. Thank you for stopping by.